we're starting the second major concept of two concepts in this class. Obviously, number one concept was differentiation and finding a derivative. Starting with what you know about the position of something and figuring out how fast it's going or what the rate of change. So tonight, we're going to go backwards. Tonight, we'll start out knowing something about how fast something's going. And from that information, we'll be able to figure out how far it went in its travels and determine where it is at the end of its travels compared to where it started. Okay? So, let's suppose that you, bless your heart, are going to the beach on Saturday with everybody else from probably southeast USA or anywhere in the near region. And you're going to drive down 59 or the Beach Express and you're going to go to the beach. But from between 10 a.m. to 11 a.m., what do you think your speed, how could you describe your speed going to the beach? Slow. Okay, what else?
Stop and go.
A lot of stop and go, stop and go, stop and go. Right. So, you know, we might consider, okay, I might start off at a positive speed, and okay, because I've got to plug up. Excuse me just a minute. And we're talking speed now. This is the rate or the speed here of the car, and this is the time. That's completely different than what we've been talking about for the past 4 weeks. We had distance up here, or position. Now we have the speed of the car. So think about its rate of change, how much its distance changes over time. So you're saying a lot of stop and go. So if I draw it this way, what's the car doing? Slowing down, because it's a rate, right? If I draw this, what's happening?
Stop.
Good. Everybody agree?
No.
Why not? Yeah, because that's good. Because we thought about distance before when we looked like this, and our distance function, we were stopped. But now my speed is constant, right? My speed is constant. What would it look like on this graph if my car stopped? All the way down to zero. Good. So we went all the way down to zero, and we're in a traffic jam, right? So we're completely stopped for a while, and then all of a sudden, maybe the traffic picks back up, and you know, on a lucky day, maybe my velocity increases until I get stopped again. All right. So the question is, if this is the velocity between 10 a.m. and 11 a.m., the question is, how far did the car travel in that hour? I mean, I knew how fast I was going. So how could I figure out how far I went? Well, to figure this out requires calculus. But let's look at a little bit of a simpler idea that doesn't require calculus so that we can equate the simpler idea with what we're going to have to do to estimate using calculus. So let's go to the simpler idea and then we'll come back to this in just a minute. So let's say you're driving on the interstate. You're on I-65 and you're driving between 2 and 4 a.m. Bless you. What happens between 2 and 4 a.m. on the interstate?
Not a whole lot.
Blow and go, right? Set that cruise and just hope you don't fall asleep. So if we're talking about velocity now, this is speed over a 2-hour period. What would the graph of the velocity look like? What kind? Straight across? And this value up here would represent what? Speed. And at 3 a.m. in the morning, you could probably go without getting arrested.
85.
85. Okay. So we're going 85 miles per hour at 3 in the morning, and we're going to go 85 miles per hour for 2 hours, right? Let's suppose that you don't have to stop, you don't have to slow down in that 2 hours. How far did you go?
170 miles.
How do you know you went 170 miles?
We went 85 miles per hour. You're going 2 hours.
So you're taking 85 miles per hour, and you're multiplying it times the time, and that gives you, what'd you say, 170? 170 miles. But that's a constant speed, right? A constant speed. And we know distance equals rate times time. Rate times time equals distance if our velocity is constant. As a picture of this idea, rate, well, just a minute. My rate for this 2 hours, anywhere in this 2 hours, I'm going 85 miles an hour, right? So all of these green segments have a length on my graph of 85 miles per hour, right? And so I've kind of drawn a rectangle, right? Kind of drawn a rectangle where the 85 miles per hour is my height, and what is my length? 2 hours. Yes, 2 hours. So what we're talking about then is that the area of this rectangle, below this blue line that represents my velocity, all the way down to the x-axis from 0 to t equal 2, the area of that tells me how far I went. Okay, you get the idea? So if this was the beginning of my trip, and this was the end of my trip, I would be 170 miles from where I started. We're coming back to this one in just a few minutes. We've got to figure out a way how to get that area under that curve, or between this curve and the x-axis is what we need to figure out. So let's do a couple more simple ones. Tell me what this graph would represent. And I'm going to start calling it velocity now. You're going to understand why in just a second. Velocity and time. We're talking about velocity functions. If I draw this graph, what would it represent? What's happening here?
Wouldn't occur in that direction.
How do you know that?
You have a negative velocity
Where do I have a negative velocity? Where's that happen?
below the x-axis.
So from here to here, whatever these times are, the value of my velocity is negative. From here to here, the value of my velocity is positive. So in this time frame, I'm getting closer to a point. I'm traveling, but am I getting farther away? I'm getting farther away from a point. My distance is growing. But from here to here, my distance is decreasing. So I must have driven for a while, and then what? And then what? Oh, past a point or what?
Or turned around.
Or turned around, absolutely. Wait a minute, what are you saying, Paul?
You could either pass it or turn around.
So what's the description you're giving of this? That there's a point, like Parker being the point, and I'm going to walk toward Parker, pass him, and when I get to him,
You're going to move farther away from him in one way or another.
but this graph right here states that at this point my velocity is 0. And for a velocity to be 0, what has to happen to the object? It has to stop, doesn't it? So if I simply walked from from here to Paul and pass Parker along the way, this is not necessarily that situation, because I might not even stop walking or slow down at all. I'm saying that right here, I'm actually going to stop. My velocity then becomes negative, so my direction is changing. I'm either rising and then falling, or I'm walking farther away and then turning around and walking the other way. So go ahead.
That definition, then, if you walk past him and didn't stop, would you have to put a hole on the x-axis?
If I walked past him and didn't stop, the question would be, is my velocity staying constant? If my velocity stays constant, then I would just have a horizontal line, because we're talking now about the velocity.
Velocity has a direction as well as a magnitude. That's why we're not talking about speed, right?
That's right. Velocity has a direction, and when you get down here to be a negative, velocity can be negative. The speed might have, when I turned around, might have still got me back up to 20 miles an hour, but since I'm going back toward that point, my velocity is negative. I think what you're thinking about...
Going toward the point or away from it when your velocity is negative?
When I'm going toward the point, because my distance is shrinking. If I'm going toward the point, my distance is decreasing. My distance is decreasing. My distance is decreasing.
If you're going toward it,
yeah, so if I'm decreasing, then my tangent lines all have negative slopes. My distance is decreasing, my tangent lines have negative slopes, therefore that's where my velocity is negative. I think what you're thinking about is the distance idea. That if, on this graph, of what you talked to me about walking past Parker, if I measured my distance from Parker, okay, I'm this far away from him now, and I walk toward him and my distance decreases, and then I walk away from him, but my distance would actually decrease if we're talking about a position function. Okay, so if this is the end of my time, right here, how far am I from here to here? How far am I from where I started?
Are you at it?
You're back where you started.
I'm back where I started. Because if we think about area now, this triangle has an area, right? That appears, if I drew it by hand, but if it appears to be congruent to this triangle, right? But since I had a negative velocity down here, I have a negative position coming back the other way. And basically, these two triangles cancel each other out. Now, how could I figure out how far I traveled total from the start of my trip going forward to coming back? To get that total distance, I could figure out what the area of this triangle is, figure out what the area, the positive absolute value of this area is, and add them together. And that'll tell me how far I traveled. But the fact that this velocity was below the x-axis, my areas might both be positive, because we know from geometry class that area can be positive, only can be positive, right? But the fact that this area is below the x-axis means that the where I started to where I ended cancel each other out. All right, let's go back to the one we looked at about going to the Gulf. So we've drawn a picture of your speed. Was I ever going backwards? How do you know? I was never going backwards. That's right. Our velocity never became negative. So I was obviously always going forward. If I wanted to try to estimate how far I traveled in this 1 hour period, what would I need to do?
Find the area?
Yes. So ultimately, I'm looking for the area between this curve and the x-axis. Now that's going to be very difficult to do with what we know so far in our mathematical repertoire, right? We don't know how to find areas of figures that have curved sides. All we know how to do is find areas of triangles and rectangles and pretty parallelograms and all that kind of stuff. So how can I estimate how far I've been? It's a big, fat, hairy idea right here.
I'm looking at it.
Big idea. How could I estimate, from what I know so far in mathematics, how far I've gone? The green area. Estimate now. Approximate. Ma'am? Tangent lines, though, would tell me how the velocity is changing. And that would be acceleration. Your velocity is changing, tells you how much you're pushing the pedal. I want to know how far I've gone. How could I estimate the area of the green region?
How fast you were going in the amount of time you were going.
Oh,
When we
yeah.
get to that, you might have
Say that again, Rachel.
How fast you were going in the amount of time you were going.
How fast you're going, your rate, times the time that you went.
Yeah.
And that's what we did here,
Yes.
when our rate was constant.
But it's changing, so like, what if you do the highs and lows instead?
So our rate is changing, so you're saying highs and lows. What do you mean by that?
Like, you start off high, then it dips, levels out, 0,
Mhm.
then goes back up.
So like do it in sections?
I mean, no, because that's not going to work out, but,
That's what you want you to say, Smith.
What would you do with those highs and lows?
you know, just, I put them together, figure it out, and times the time.
So now get an average rate of speed?
So
Yes.
so you're picking velocities, like your high velocity, your low velocity, pick a few velocities to get some estimates and multiply it times your time. What time?
You don't know
Would you multiply it by 1?
the overall time. So, yeah, what,
2 hours?
Yeah,
yeah.
1 hour.
So if I took my velocity, let's say that I was going 55 miles an hour right here. And then I was going maybe, I don't know, let's say 15 miles an hour right there. And then of course that's 0, and let's say I ended up here at 50 miles an hour. So are you saying that you want me to take some velocities and add them together and then multiply by 1?
No, you gotta
Break down the hour.
You gotta what?
Break down the hour.
Break down the hour. How do you mean?
Well, increments of 15.
Increments. 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 You want to do 15 minutes? All right, so 15-minute increments. So that would be 30 minutes. This would be 2 15 minutes, right? So I've broken down the 1 hour into 15 minutes, got the increments. Now what do you want me to do?
Well, your increments are figures.
Say it again, Rodney.
And your increments just separate figures.
Okay, and what do you want me to do with those figures? So you want me to split it up into pieces?
Right.
Okay, I'm splitting it up. I'm splitting up my green region into pieces. Keep talking. I'm looking for the area of the green region. Looking for the area of the green region. It's got curved sides. Y'all talk about it. Talk to each other. Help me out here.
15 plus 5.
The point is, do you know how to find the area of a region that has a curved side if it's not a circle? We don't know how to do that, do we?
No, just estimates.
That's right, estimates. We only know how to find the areas of what's? Triangles, rectangles,
Polygons.
geometric figures, right. So if I want to estimate,
Make one.
make some rectangles.
Yeah, you do.
Let's make some rectangles. Let's split it up into 5-minute segments. How about that? 5-minute segments. And in those 5-minute segments, let's draw rectangles. Now this purple rectangle, its area will be an underestimate. Do you agree?
Yes.
It's not going to be enough as far as the distance, but it'll be a pretty stinking good estimate. Then we'll draw, and what would we multiply? We would multiply whatever that value is. Okay, we could probably estimate that at about 45 times 5 minutes. 5 minutes, 45 miles per hour times 5 minutes. We have to do some conversion in there to figure out how far we've gone in that region. And then we would keep this up. Right?
Would your final answer be a plus or minus?
We would know that it would be an approximation, but we would not know how much we're off. I mean, it really all depends on, our approximation depends on what? How good, our precision depends on what?
How small the increments are.
How small the increments. Say it loudly.
How small the increments are.
Yes. And we're going to be pretty stinking accurate if we can draw 50,000 increments. Well, that's not good enough. Let's draw 100,000 increments.
You're going to try to get something that are infinitely
Are you Edmund?
small in the exponent.
Edmund, I'm sorry, you're not a fan, so we speak the same language. But I looked at Edmund and he was going, please don't make me draw 100,000 increments. Amen, brother, I'm right there with you. I don't want to draw 100,000 increments. Are you ready? Calculus allows you to draw millions of increments without actually having to draw them. It's a wonderful thing. Okay, you get the idea? Right now, in the beginning of our lesson tonight, we can only estimate. But in about 30 minutes, we're going to get to a place where we can find the actual area under this curve. So let's hang out with the approximation business for a minute, and then you'll know when we move over to the idea of actual true values. So let's go do some more approximations. We're still in the approximation stage. We're doing no calculus yet. I mean, this is just an idea right now, using what you know about pre-calculus. So here I've got the function y equal 1 over x. There it is right there. This is the function y equal 1 over x. And it is marked off between x equal 1 and x equal 2. And below this red curve, I've got a shaded region. But you notice that there's a couple of different types of rectangles drawn. There's rectangles that are drawn below the curve. Do you see them? The purple ones are below the curve. And in this case, I've got one, in every case basically when we're finding approximations, we want one corner of every rectangle to touch the curve. And we want every rectangle to be divided into equal increments. So if I found the area of all the purple rectangles, I would have a low estimate or a high estimate. It would be too little, wouldn't it? Because I've got these little pieces here that would not be included. So the purple represents the lower sum. Let's talk about how to find that lower sum. How to find the area underneath that red curve using lower sums between 1 and 2 using 5 increments. So, if I'm going to find that area, I need to do what? If I'm going to find the total sum,
You gotta know what your y and x are.
know what the y's and x values are. So how about the increments? What would they be?
0.2.
Delta x.
0.2, each one of them is 0.2. So the width of each rectangle is 0.2. Do you agree? No? I've got one hole divided by 5 segments. Is that 0.2?
Yes.
Okay. So each little interval is 0.2. So I'm going to multiply 0.2 times the length of each little rectangle. And I'm going to have 5 of them. All right? This is the width of every rectangle. Now I've got to determine what the height or the length of every rectangle is. So, I'll mark it in yellow. This first rectangle has a height this high. The first rectangle has a height that high. How do I know that that's the height and not the left-hand side of the rectangle? That's where it touches the curve. That's the key. So the question now is, how do I figure out how high that yellow, what's the length of that yellow segment? Because that's what I need to put right here. Help me. How do I find the height of that yellow segment?
Break up the Y.
Oh, use the equation.
Oh, break up the Y this way?
That's a possibility, or I mean, it could be estimation.
Just use the
Use the equation.
Here?
Yeah.
So we were told what Y equals at any X value, right? So the question is, what's the X value right here where the yellow starts?
1.2.
1.2, isn't it? So if this right here is 1.2 units long from the origin, then the yellow length must be 1 over 1.2. Absolutely. 1 over x is my function. The x value right here at the bottom of this yellow segment is 1.2, so the height must be 1 over 1.2. What's the next one? 1 over 1.4. How about the next one?
1.6.
1 over 1.6, and then
1.8.
yeah. And this is going to give me a lower sum. It's going to give me an approximation for the area under that curve, but it's going to be too small. Okay? So now what about the upper sum? I'll draw the upper sum rectangles in green. The upper sum rectangles would still be rectangles where one corner has to hit the red curve. One corner of the rectangle has to hit it. So here might be the first rectangle. You see how one of the corners hits it right there? And then I've got all my corners of each green rectangle hitting that red curve. Okay? So for the upper sum, we're kind of going to do the same thing. For the upper sum, we'll still take 0.2 times a height, and we'll do this 5 times. 0.2 being the constant width of every rectangle. And I need 5 of them. But this time, yes sir?
For the sake of simplicity, could you factor out the
Absolutely. So to add up all your heights, good William, you would add up all your heights, that would be your total height of all the rectangles, and then just multiply your sum by 0.2. I think you actually used the factor out 0.2 word. Absolutely. Add up all your heights and then multiply by your common consistent interval or width. But here in this case, as I've written them all out long-wise, this first rectangle in green has a height in red right here. I don't want to use red, I'll use yellow again. Right here. There's the height of that first rectangle. Why is that the height now and not over here on the other side like it was before? That's where the rectangle meets the curve. How big is this yellow region, this yellow segment? 1. How big's the next one?
As big as
1 over what?
1.2.
1 over 1.2. How about the next one? 1 over 1.4. And then 1 over 1.6. And lastly, my last one would be 1 over 1.8. That's going to give me an overestimate. That approximation of the area of the curve is going to include these little triangles up here at top, which aren't part of the area under the curve. So I know I'm going to get a bigger value here. So, you know, we could, if we wanted a good estimate without using calculus, we could find both of them, maybe find an average, right? Average them together. Or, you know, if we really wanted to do a lot of work, we could, somebody said a while ago, split up your intervals into a bunch more rectangles. William?
Well, if you just subtract the lower sum from the upper sum, and then, never mind, I don't know what else then.
But finish your sentence. If you subtract the lower sum from the upper sum, you're literally only going to get what as the area, as what area in this region?
The short upper part.
Yeah, you would only get these little ones right here. Absolutely. So you got to pick one or the other, or do both and average them together, right? So upper sum and lower sum. Probably the hardest part about these two is trying to figure out where to draw the rectangles if they're not already drawn for you. What you need to consider is that the rectangle top corner has got to touch the curve. All right, so let's get to the good stuff. I don't want to have to draw rectangles for the rest of my life. Please don't make me draw rectangles every time I want to find how far somebody's traveled if I know their velocities over the trip. And we're talking about variable velocities, velocities that change. That's all we care about. If the velocities didn't change, we could just find an area. So let's suppose that you have done some type of a study and you know that negative 4x squared represents the velocity function of some movement. Okay? This is the velocity. This is f prime. I want to know what f equals. I want to know the position function. The position function is f. So it should make sense now what I was talking about now about going backwards, right? For the past 3 or 4 weeks, you've been given f and you've learned how to find f prime. Now you're being given f prime, or the velocity, and you want to go back the other way and figure out the position of the object. So can you look at this and tell me what function would you be taking the derivative of to get negative 4x squared? Just holler some things out and we'll just test them.
Something to the
third.
Yeah.
Something to the third, all right? What else? He's using the power rule backwards.
Negative number.
What do you think, William?
What if there was a constant in that original function? I mean, it's impossible.
Your question was so freaking good. Wait, I have to get this on video. William Clark just asked, what if there's a constant?
I'm failing calculus, by the way.
But he understands. Why did you even make that statement?
Well, I mean, if you're trying to find the original f of x, I mean, it's doing f of x with constants. You just eliminate the constant. Constant equals 0.
When you take its derivative.
Right.
So you mean I could add a 52 right here?
Right. So now, if you just have f prime of x, you can't pull 52 out of nowhere. I mean, it's gone.
Are y'all following him?
0. So
If we're going backwards, right, and we're trying to figure out the I'm not done here. I got a question mark right there. If you're trying to figure out what you're going to take the derivative of to get this velocity function back, there could be any constant here. I have chill bumps. That is, I mean, I have chill bumps. That is so freaking great. You're right. We don't know what the constant is. That's why. Wait for it.
C.
We let that constant be called C, because it could be anything. We don't know what that constant is. We have no idea. We have no idea how far away we started, but we know what the movement was. We don't know. I need something to go in place with the question mark.
Negative 4/3.
Negative 4/3. Let's test it. Let's see. Would that work? If you took the derivative of this function, would you get that function back? No matter what number was here in the place of C, you would get that back, wouldn't you? How'd you do it, Nick?
Figured out, I divided negative 4 by 3.
And then multiplied it by 3 to get the derivative. So you were having to fill in a hole here to try to figure out what you needed to put here to get back to that velocity.
Right, well, you subtract the exponent by 1, so you know it's got to be 3.
Okay.
So you're going to then multiply it.
Oh, so you knew this had to be a 3, so you were using the power rule, and so the 3 was coming down front, so you had to figure out what had to be on the bottom to cancel it out. Okay.
It seems to me, since you're going backwards, like when you're taking the derivative, you just take the exponent, multiply it by the constant, and then take the exponent minus 1. This time you do it backwards, you add 1, and then take that and then divide it by the constant by the new exponent.
So Austin, are you trying to come up with some shortcuts?
I guess. That's
Hallelujah, brother. I want some shortcuts too. Okay, so we're going to come up with some shortcuts. Everybody loves shortcuts, but the notation will look like this. Let me make sure you understand what we've done here. I gave you the derivative. I gave you f prime. And in calculus notation, that's dy dx, right? Now, if I multiply both sides by dx, this is called a differential equation. This is the differential equation. It tells me on one side how much my position is changing, how much the position changes with respect to time on this side. Then what I'm going to do is find an antiderivative. Nick just helped us find an antiderivative. We've been finding derivatives for weeks. We're going back the other way, and that's called an antiderivative. It's also called an integral. So this is what we're going to be using to find, the process we're going to be using to find antiderivatives is finding integrals. What you have just discovered is that when I take the integral, excuse me, I need to make very more specific. When I take the integral of both sides here, when I take the integral of dy, that's going to give me my function. And when I take the integral of negative 4x squared dx, that gives me the negative 4/3 x cubed plus c. So we could have any constant and take the derivative and get 0. So now what I want to do is talk about these shortcuts for a moment, because I do have a shortcut sheet for you. And I want to make this go away, and I want to make it a little bit bigger, and I've got copies for everybody. We'll talk about the shortcuts for finding antiderivatives, and then talk about how we're going to learn to use those shortcuts to find antiderivatives.
Are these the opposite of the
Not really. You would think that would be the easy case, but no. Nick asked, are these just the opposite of the derivative formulas? Not in all cases. Some of them are, but not in all cases. For instance, we don't have a chain rule for antiderivatives. Some of y'all are cheering inwardly at that. But if we don't have a chain rule, then we need something else that we're going to use when our function doesn't meet any of these rules. So let me take a minute to describe to you what I've got here. So the first one, I'm simply saying that if you're trying to find the integral, here's your velocity function right here, velocity function. So everywhere you see an f of x, we're just taking the prime off. And now today, you're assuming that the f of x and the g of x are the velocity functions, and we're going back to try to find an antiderivative. I've got a constant times a function. So this first rule simply states, that you can take that constant and pull it to the outside of the integral. Oh, sorry, just grab them all. You're going to take the constant, pull it out front, and then you're going to take the integral. So if you know, we did kind of have that with derivatives, didn't we? With the constant multiple rule. You held on to the constant for a while, and then you took the derivative of your function. Same thing with integration. If you're trying to integrate a constant times a function, pull that constant out.
Would that be considered factoring? Okay.
You could call it factoring out a k if you want to. We can take out a k. The k is not going to have any bearing on our antiderivative. Now this second one, the integral of dx is x. Well, what's the derivative of x?
1.
Yes, so there's actually like a little hidden 1 right here. If you want to write it there, you can write it. If the derivative of 1x is 1, then the antiderivative of 1 dx is x. Of course, plus c. If you take the derivative of c, what you going to get? 0. Here, this is what Nick was talking about, is antiderivatives just backwards derivatives? Yes. Yes. But check out this one now. The derivative of, what's the derivative of cosine?
Negative sign.
Negative sign. So if I've got cosine here, and I take the derivative of cosine, what's the derivative?
Negative.
And then I multiply that by a negative, what do I get back?
Positive.
That's my sign. That's what I'm taking the antiderivative of. Secant squared is backwards derivative. Secant tangent is backwards derivative. We'll get to these down here on the bottom next week because they take a little bit more work with inverse trig.
On the sine and cosine would be the same thing as if you had a -1 in front of the sine, I guess. Right?
Say that again, Mike.
Like if you had a negative, how the first one, you just move the k to the front.
Right.
You had a negative.
Yeah, absolutely. But these are just the basic formulas. We're going to be finding antiderivatives of functions that aren't on this page. So we are going to have to figure out which rule are we going to use and how are we going to use them. That's the whole point of the rest of tonight's lesson, is figuring out how to use these basic rules to find antiderivatives. What does this one tell you?
Addition.
Product or the
So give it to me in your own words. What's this telling you can do, that it's okay to do? Just what, William?
Distribute the integral.
Not necessarily.
It's like the addition formula for derivatives.
Right, you can split, yeah, we could split up derivatives with a plus, we could take them apart, but if you're taking the derivatives of terms, then you can take just the single derivatives of each term. Same thing here, you can split it up with a plus. This is what Austin was talking about. Check it out. If I'm trying to find the antiderivative of x cubed, he's saying take your x, add 1 to the exponent, because if you were taking the derivative, you would have to subtract 1 and then divide by n plus 1. Okay, so the goal of tonight is to figure out how to use all of these rules, how to use them, when to use them. And I'm going to tell you people, this is all we've got. This is it. There are no other rules but this right here. This is the basis of part 1 of your quiz next week. Your quiz next week comes straight off of this page. Do you know your basic antiderivative rules? No, they'll be on there too. You need to know them all. You're going to need to know all these next week. Just plug and chug, just regurgitate these for part 1 of next week. The second part of the quiz next week is learning to use these rules. Yes, sir?
What about arc cosine?
We may add it along the way. We may add it like we did last time. Okay,
So
so
that one's not going to be on next week?
not going to be on next week. What all you see right here is going to be on next week's quiz.
I just cut it off there.
And for those people watching on the video, your quiz is on the 14th. Your quiz is on the 14th, not next week. We won't see each other next week. So here we go. I want to find the indefinite integral. Now let's talk about that notation. You know what integral means. That just basically means let's find the antiderivative. Indefinite goes along with what William Clark was talking about earlier. there are an indefinite number of constants that we could add to this antiderivative, right? This plus C idea tells us that there are an infinite number of antiderivatives because you could add any constant to it. So this, when you're looking for an indefinite integral, that means you're looking for the plus C, that your antiderivative will definitely have a plus C on it. All right, you got your rule sheet there in front of you. Tell me which of these rules on your sheet, and hey, let's number them. Let's number them so we can all be talking about the same thing. Let's number down this way. And if you yell out a number, then I'll go back and look at it. Which one would you like to implement first?
8.
Number 8. Why did you choose 8?
It's a bunch of terms being added and subtracted.
So he sees subtraction and addition. Everybody see it? So that means that I can use rule number 8 to split this up into multiple integrals. Multiple integrals. Okay? Got it. Notice that I'm taking sorry. Thank you, that's yours, Rachel. Notice that I'm taking the antiderivative symbol with me because on rule number 8, on the right side of the equation, in rule number 8, the integral symbol is still there. It's just telling you how you can split up your integrals. The symbols make a difference. I am very picky about notation. So know when the symbol goes away and when it doesn't. What would you like to use next?
9.
Number 9. Number 9. Okay, tell me where you see this.
The 8x cubed.
Yeah, but there's an 8. In other words, if you use number 9, you should only be looking at the integral of x cubed.
Well, 9 plus 1.
Oh, you want to use number 1 first? What does number 1 tell me I can do?
Move the 8x.
Move what to the front?
The 8x cubed.
Look at it again. Just the 8. Just the constant. So if I'm going to move the 8 out front, I'll move it 8 times the integral of x cubed dx minus 9 times the integral of x squared dx plus 4 times the integral of dx. I haven't done any integration yet, really. I've done no calculus. I've just rewritten it so that I can get everything in terms of the sheet. I'm going to start over here on the right-hand side. Look at the integral that I have outlined in red. What rule is that? Number 2, isn't it? It is specifically number 2. That integral of dx is exactly what is on that sheet. And the integral of dx is?
X plus C.
X plus C.
Now, is that 4 times x plus c?
It is, sure is. 4 times. I need a 4 here. Yes, I do. That one's yours. 4 times x plus c.
Do we need parentheses there?
Do I need parentheses? Why not, Corey?
Because that's
It could be 50 or it could be 50 times 4, 200. It really doesn't matter, does it? So you do not need parentheses. How about what's outlined in blue? What rule are you going to use?
That's going to be 9.
Number 9, she says. Everybody agree this is number 9? So I've got the integral of x to the nth dx. And what is the integral of x to the second dx? I'm looking for the antiderivative.
X times 2, or x is 2 plus 1
That's 3.
over 2 plus 1.
That's another 3. And then of course
Plus C.
that's all multiplied times 9. And then you want me to add c?
Right.
Another C? You mean add another C? Why is there no point?
All the C's can be combined. It doesn't matter.
Yeah, combine them all together and just call it one big fat constant, because it really doesn't matter what that constant's value is. If you find its derivative, you're still going to get 0. Even if you had 50,000 C's here, and you take the derivative of every C, you're still going to get a bunch of zeros, right? William?
Are we ever going to find out what the C is?
Wow.
It's killing you.
Is it the Spence is killing you? You want to know what C is? Yes, we will. We will actually have, we might not know exactly what C is, but we will have a situation where C does not apply. Okay?
In the future, will we need to keep track of all the C's that we have? Like, will they be important at all?
Well, if you're taking an indefinite integral, Austin, an indefinite integral, you only need one C in your integral, because you're just taking the derivative of a constant that'll go back to 0.
Do we need to keep including the dx's, or do we need to even include it in the first place?
I do not. Yes, you do need to include the dx's in your differential equation, because you're integrating a differential equation. And so when you take the integral of a differential equation, you get the function back. Yes. If you don't include the dx's, then what we do tonight at the end will cause you issues. You definitely need to keep up with your dx's. And hey, the problems you will have in encountering calculus 2 if you leave that off will be enormous. How about the x cubed?
Same.
Same thing? What would you like for me to write?
4 over 4.
Okay, so I've got x to the 4th over 4. I'm multiplying that times the constant, and then of course I'm bringing down this minus. So in simplest form, my antiderivative is 2x to the 4th minus 3x cubed plus 4x plus c. My antiderivative. How can I check it?
You take the derivative?
Yeah. The derivative of this is 8x cubed. I had an 8x cubed. The derivative of this is negative 9x squared. Show enough, that's what I've got. The derivative of 4x is 4, and the derivative of c is 0. Now, you're going to get so stinking good at it that you're pretty much going to be able to leave off these steps, okay? But my job tonight is to make sure that you're not guessing, that you're not making up your own rules, and that you know what rules I'm using from the rule sheet that you're looking at. Okay? Let's try another one. We're practicing finding antiderivatives, specifically indefinite integrals, using the shortcut formulas. Rodney, you want to use number 3? Rodney held up 3 fingers. I need to go back and look and see what rule number 3 is. All right, Rodney, everybody look at number 3, and let's compare what we're doing to rule number 3. So Rodney, if you use rule number 3, let me be very specific. What you're looking at right here has to look exactly like what's on that paper. And it doesn't, does it? Then I can't use the rule. This does not say the integral of 1 over x dx. It says the integral of 1 over x to the 6th. That rule is out of play. What other ideas do you have?
9.
Number 9. Oh, sorry, I'm going the wrong way. Number 9 is the quote-unquote power antiderivative rule. Now, okay, if you use number 9, how do you want to use it?
X to the negative 6.
Oh, so you want me to use algebra first. You want me to use algebra to rewrite this statement. What do y'all think?
Sure.
Yeah, I mean, if you're going to use the rule x to the nth, this integrand is not in the form x to the nth yet until you rewrite it with algebra. Now rule number 9 is legal. Now I'm about to take the antiderivative. We are about to use that sheet, and when that happens, the integral symbol disappears. So as I use the rule, I'm adding 1 to -6, so that's -5, divided by -5 with a plus C. You can enter it into WebAssign just like this, or, an equivalent form would be -1 over 5x to the 5th plus C. That'll be perfectly fine, but it will take, remember, all equivalent forms will be just perfect.
Are we always going to need to do that with division?
Yeah. Are we always going to have to do that with division?
Because we could have done that with
You will always have to do something with division. It might not be this, but you will. In other words, what you're saying, Nick, is we have no division on this sheet except here, here, and here. Is that what you're saying? So if we are given an integrand and we're trying to find an antiderivative that involves division, we got to do something. It might be this, what we just did, or something else.
But it's usually going to be a negative, turning it into a negative exponent.
Well, it depends on what the division is. I'm not going there. I'm not going to get backed up in that corner because I know what's coming. All right, how about this one? Basic antiderivatives is what we're doing now. Basic. You're starting to get good at it. Holler out some ideas. What is number 8?
Separation plus.
Split them up, okay? So I've got the integral of 3x squared dx plus the integral of 2e to the x dx. So all we did, we haven't done any integration. We've just used the rule that allows us to split up our two pieces. Okay?
Step 1 brings coefficients out.
Number 1, bring out the constants as coefficients. Good. We're ready, aren't we? I've got, if you look at the integrals, I've got one in blue right here. Hey, that looks exactly like number 10. And in red, I've got another one right here, and that looks exactly like number
10.
That's number 10? This is number 9.
Okay.
So we're ready. When we get our integrals to look exactly like the sheet, then we're ready to find an antiderivative. Not until then. Look, do you see my exuberance here? That you're going to feel like I can just make up a rule. And it is going to be it's going to feel so good to make up your own rule. But I'm telling you people, if it's not on the sheet, you cannot use it. So I've got 3x cubed over 3 plus 2 times e to the x. And what else? Yay, plus c. The derivative of any constant is 0. So in its simplest form, our antiderivative is x cubed times 2e to the x plus c. Do you notice when I dropped the integral symbol? From here to here, the integral symbol was dropped. From here to here, I used the sheet, didn't I? When you use it, and you refer to it, and you use the formula, the integral symbol's gone. But not until then.
So pretty much whenever we get our answer, all we have to do is just look at it and make sure it looks just like the beginning.
When you find its derivative.
Right.
Right. Derivative is 3x squared, check. Derivative is 2e to the x, check. Derivative is 0, absolutely. Hey, it's easy right now, isn't it? Is it feeling good? It's going to get hard in a minute, so just hang on. But we got to crawl before we walk. We got to walk before we run. Okay? Maybe?
We need to break rule number 3 for separated and we need rule
3, separated into what?
3. Separated the 4 over x plus the secant squared.
Okay, so we're going to separate it into the integral of 4 over x dx plus the integral of secant squared dx. And you're going to probably learn to
Do it all.
skip that step, but I'm afraid to skip it right now.
Can we take the 4 out?
A 4 is a constant. Who am I talking to? Bronwyn? Good. Taking the 4 out. And Bronwyn, when you take the 4 out that's a constant, what are you left with?
1 over x.
Good. 1 over x dx. Good. So do I need to bring the x up and rewrite it as x to the negative first? And actually that would cause a problem, wouldn't it? Because when you try to then use rule number 9, you're trying to divide by 0. That's bad. Hey, by the way, have you asked Siri lately what 0 divided by 0 is?
Yeah,
she
did
said
that
you
last.
were losing.
I just thought it was fun. I did it
You
this
said
morning.
you were friends.
Okay, so here we go. 4 times
Oh.
Natural log of x.
natural log of x, and actually it's a natural log of absolute value of x, because if x is negative, you can't take the natural log of a negative number. Plus,
Tangent of x.
the derivative of tangent is secant squared, so the antiderivative of secant squared is tangent
Plus c.
plus c. Good. Now, I got a break built in somewhere in here. I promise I do. There is a break coming up in a minute. So now let's talk about a definite integral. A definite integral. So now we've learned how to find antiderivatives. So now we're going to use what we learned there with the sheet and go back to this idea of area under a curve. Because for this last segment where you learned how to use the sheet in indefinite integrals, that had nothing to do with area under curves. But now as we go back to area under curves, we need to discuss something called a definite integral. Now before I do it, I need to talk about a very important theorem. And I'm going to come back to this page. A very important theorem that allows us to find the actual area under the curve, as if we had split this area up into a trillion rectangles with little bitty widths that are so small that you can't even see them. And that important theorem is called the fundamental theorem of calculus. Hey, it's called the fundamental theorem of calculus because it is a big, fat, hairy deal. And it allows us to find the actual area under a curve. What?
Is this one important?
Important. The fundamental theorem of calculus. So let me talk about the notation to you first. You know about the integral symbol. And you know about the f of x dx. So what you're looking at here, there's your velocity function. And so you're trying to find the function for which this is the derivative. That's the antiderivative stuff we've been doing. But this a and b, those are the boundaries. Those are the boundaries for your variable. That's where x starts. Here's your start. The bottom is always your start, and the top is always your end. Now the reason I know these are x values, these are x boundaries, is because I'm integrating with respect to x. You could always integrate with respect to y as well. But this letter right here, The D letter, that letter tells you that these two values are x values. If it said dy, then these would be y values. And you would have a bottommost boundary and a topmost boundary. Y and y. So the fundamental theorem of calculus is so fundamental that I don't want to screw it up. So just a minute, let me look at my notes. Okay, big F is going to represent the antiderivative. Big F is the antiderivative of little f. You know how to find antiderivatives. The fundamental theorem of calculus states, find the antiderivative, evaluate it at your uppermost boundary. Find your big F, your antiderivative, evaluate it at this value. Plug that value in for x. And then subtract from that your antiderivative evaluated at your lowermost boundary. And that idea will take care of the need that you won't need a C value anymore, because you're actually looking for you've got actual boundaries, and you know where your function is. You know where your graph is to start with. So let's go back. So in this case, my function is f of x equal to cosine of x. I have it drawn from 0 to pi over 2. I want to set up the definite integral that yields the area. And let's just go ahead and find the area, since we already know the fundamental theorem of calculus. So the area here is going to be represented by what integral? What's my velocity function now? I'm given the velocity function. Even though it says f, we're going back the other way now, and we realize that since we're looking for the area under a curve, we know that we're given the velocity function. All right, so I got the cosine of x. X is my variable, so I need a dx. That's an indefinite integral. Indefinite. I want a definite integral.
Start reading.
Sir?
You got to put your start.
My start and my end. And my start and my end, will I go from 0 to 1? Or will I go from 0 to pi over 2? Or does it matter?
Pi over 2, you're on your x.
It matters because you subtract.
Because it's x values, isn't it? It's x values. My variable that I'm integrating with respect to is x. Therefore, my start and my end represent x values from 0 to pi over 2. Okay, you're about to see why the C doesn't matter. I know some of you don't believe me that I can leave off the C, but I'm going to enter the C in it while we're doing this so you can see what happens to it. What's the antiderivative of cosine? Sine of x? You're using a sheet, right?
Yes.
So I'm going to take the integral symbol away. So the antiderivative is the sine of x. I'm using the fundamental theorem of calculus. I have already taken the antiderivative, so I can't use this symbol anymore. To notate that I'm evaluating from 0 to pi over 2, I don't want to lose these values. I'm going to put a vertical bar on the right side of the sine of x, and I'm going to note my boundaries here. So I've got the antiderivative, big F. Here's big F right here. Little a, big B. Excuse me, little a, little b. So the fundamental theorem of calculus states that I need to evaluate the sine of x at pi over 2. Hold it, wait a minute, just a second. I told you I was going to put the C in there. Let me put the C, just so you're going to see what I'm talking about. Just add a little plus C. She used the sheet, and I didn't put the C down. So I've got the sine of pi over 2. Little b, evaluate big F at B first, plus C. And the fundamental theorem of calculus says that we're going to subtract from that the sine of 0 plus C. So what happens? Yeah, the C's cancel out, don't they? It's going to happen every time. I mean, whatever this constant is right here, if you use the fundamental theorem of calculus, these two constants will be equal and your C's will disappear. So when you're finding definite integrals, you can pretty much leave that plus C out because you're going to have a numerical value. We really don't need these plus C's now. The sine of pi over 2 is what? Root 2 over 2? No. 1 minus 0. What equals 1? On this, what represents that 1? The area. That pink region is exactly 1 square unit big. That's what we've just found. If we took this region and we split it up into little rectangles and we tried to approximate by finding the area of all those little rectangles, we would get something pretty close to 1. But the exact area underneath that curve is 1 square unit. All right, let's try one more. Let me see how far we are from the break because y'all are looking pretty tired. 2 more problems and then we got a break. This one and the next one. Same idea. Set up a definite integral that yields the area of the shaded region. My function is f of y equal y minus 2. My variable, now many of y'all might have never done functions of y, but all this means is that you pick a y coordinate. If I picked a y coordinate, like if I let y be 2, when I let y be 2, and I 0 back, right, for x. So, sure enough, there's a point on this graph where x equals 0 and y equal 2. So your independent variable is y. This is a function of y. We have lived in the world of functions of x for years. This just takes everything up on its side and you're plugging in another coordinate for your points. But the fact of the matter is that since I have a function of y, that does give me a clue, as Rachel said, that I probably want to integrate with respect to y. If I'm integrating with respect to y, my boundaries will be y values.
So 0 and 2.
Good. Lower to upper. Lower to upper. And then my velocity function is y minus 2 quantity squared. There's the setup that will help me find the area under that curve. So, it's a definite integral, so I'm not going to have to worry about the c's. The c's will automatically cancel themselves out, and I'm actually looking for a numerical value. Help me now find the antiderivative of y minus 2 quantity squared. You're looking at your sheet of formulas.
We start with
Number
number 9.
9.
Yeah,
Oh, but I gotta go back. Number 9.
the exponential.
Okay, I see number 9, William. How would you like to use number 9, which is kind of sort of like the power rule of antiderivatives?
Yeah.
Let me ask a question. Did you choose 9 because of the power?
Yeah.
Okay, so I can see why you would say that. But that number 9 rule says x to the nth dx. So if I was going to use that rule here, that sucker better say y squared dy period.
What do we use number 8?
What's number 8?
8 is the addition subtraction.
Splitting it up? Okay, so I have subtraction.
But when you split it up, you carry that squared power to both sides.
Oh, or sorry, wait a minute, this is big. This is big, just a second. Are you saying to me, William, that y minus 2 squared is equal to y squared minus 4?
When you split it up. No?
Oh. Y squared minus 2 quantity squared is actually equal to what? Yeah. Y minus 2 times y minus 2, which is what?
Oh, it's a quadratic.
Yeah, y squared minus 4y plus 4. Oh, so we can rewrite y minus 2 squared as y squared minus 4y plus 4. Now that allows us to split it up with the pluses and minuses.
We really don't like
So what?
We really don't like multiplication or division with antiderivatives.
No, because there is no product rule, is there?
No.
There's no quotient rule either.
No.
Did you ever think the day would come when you were wishing for a quotient rule? Okay, I'm about to take the antiderivative. Do you need me at this point to split this up into its pieces with pluses and minuses? Can I skip that point now? That part? So the antiderivative of y squared, are you good enough to tell me what it is?
Cubed over 3.
Y cubed over 3. The antiderivative of 4y to the first. I heard it right here. 2y squared. So 4 times y squared over 2. Y'all all right with 2y squared? You know where I'm getting 2y squared?
Yeah.
Okay. And the antiderivative of 4.
4x.
4y.
Y.
Okay, and I am evaluating, now I've used the sheet to find my antiderivatives. I am evaluating that from 0 to 2. My integral symbol disappeared because I used the antiderivative formulas to find the antiderivatives. That's when the integral symbol disappears. Which one am I plugging in first, the 2 or the 0?
2.
The top first. That's 8/3 minus 8 plus 8. And then minus, okay, well the rest of it will just be 0, won't it? So 8/3 is the area between our cosine curve and the x-axis, from 0 to pi over 2. What do you think? William?
I got it.
One more before the break. No graph associated with it.
Don't need one.
That's right. We don't need one now. We know what we're doing. The integral of x plus 1 over x from 1 to 5. Is it an indefinite integral or a definite integral?
Yeah.
Why is it definite?
We got one guy.
We've got boundaries. We won't need to see. If it's a definite integral, will my answer, quote unquote answer, have x's in it?
Yes.
No, you need to find
Maybe,
some
maybe
numbers.
not.
When we plug in numbers, aren't we, Anna? Anna says no. You might find an antiderivative, but and your antiderivative will have x's in it, but then you'll be plugging in the 5 minus plugging in the 1. You're going to get a number back. Definite integrals are like finding areas. You're going to get a number. There won't be any x's left. Help me find the antiderivative first, though.
Factor an x at a time.
How would you like me to do that? Help me to understand.
1 plus 1 over x.
Oh, so you want me to rewrite it?
Yeah.
He wants me to rewrite this as x over x, which is 1. Is that what you mean? 1?
No,
No, what do you mean?
no.
X times 1.
Yeah.
X times 1 over, x times 1 plus 1 over x. Over with x. And you can factor out the x's.
Wow.
Yeah, it did. Cancel.
Can you just separate it?
Oh, okay.
All right.
Your brain works in mysterious ways. I like it. This is Nick's brain on math.
What's your brain?
My brain is taking this expression and rewriting it as, my brain's 4th grade math, okay? Taking x over x plus 1 over x is the same thing.
Yeah, with
Isn't it?
that.
Like a common denominator? It's the same idea, right? Okay. So can I write this as 1 plus 1 over x? Well, why do I need to do this? Why do I need to rewrite this integral in another way?
So it's not.
Why is it harder the other way?
It's not on that sheet, is it, Rachel?
It's not.
X plus 1 over x is nowhere on that sheet. Anywhere. We've got to do something to this integrand to be able to get it sheet worthy. So, is it sheet worthy? What's the antiderivative of 1 dx?
X plus C.
Okay, but since it's a definite integral, I don't need to worry about the c. Remember, the c is going to cancel out since it's definite. Plus, do you know the antiderivative of 1 over x dx?
Or L in absolute value of x.
And I won't need absolute value here because my boundaries are both positive. And you're only going to need absolute value if you're trying to plug in boundaries that are negative. And then, what do I put? Do I put the integral symbol or do I put the vertical line? Because I've used the formulas from 1 to 5. Okay, so which one do I plug in first?
5.
So 5 plus the natural log of 5 minus, and the minus comes from the fundamental theorem of calculus, 1 plus the natural log of 1. You could leave it if you want, but WebAssign will give you this in the key. Why will WebAssign simplify it to that, or how is that possible? The natural log of 1 is 0 all day long. So this is the simplified version. And just to whet your appetite, while you're at your break, what are we going to do when we can't use algebra to make our integrand be sheet-worthy? Because we don't have any more rules, people. There are no more integral rules. This is it. So we've got to come up with some other type of a process. Be back at 7 o'clock. What would you do to integrate this? Or let me ask this, what would you try?
Taking a second derivative.
Okay, tell me why you would want to do that.
Because I'm a glutton for punishment.
But I'm not taking derivatives.
Well, this is just a
I'm taking antiderivatives. What?
Is this indefinite form?
Sir?
Is this indefinite form?
This is an indefinite integral here because I don't have any boundaries. What would you attempt to do to find the indefinite integral?
Set it equal to 0.
Why?
Because you want x, you want to find that x value because you want to find a c value. Well, just 7.
It's just an integral. It's just an antiderivative.
So don't do that.
Let me ask this question. Is the formula for this one on your sheet?
use algebra.
You got formulas for
So we're going to try to use algebra. All right, so let's try to use algebra to algebratize it so that we can make it sheet worthy. What would you attempt to do?
the
Bottom?
Make it 1/3.
Oh, okay, so pull that up top. Make it 1 minus x squared to the negative third.
Oh, yeah, then you just use the chain rule we don't have.
We don't have a problem.
I don't have a chain rule, that's derivatives.
Yeah, we don't have it.
Yeah.
We don't really need it though.
Then you got.
I don't have it, I don't have boundaries. I don't have boundaries, so I can't use the fundamental theorem of calculus.
No, like,
Right, can we get boundaries? Yeah, you gotta break it down.
can't you do that cube root rule where it's like a minus b? It's like a big rule.
Like the, are you talking about,
A minus b, another parentheses.
you're talking about the binomial theorem? Hey, you know what y'all are doing? You're talking yourself out of using algebra.
Multiply it out.
Really? You really want me to multiply it out?
I don't.
Please don't make me multiply 1 minus x squared times itself 3 times.
There's a 1 in front of it.
And even if I do multiply 1 minus x squared times itself 3 times, I'm still going to have to use the distributive property then, right? Please don't make me do that.
And tell us what was-
Wait, I can't use the distributive property. No, I can't. Because if I multiply 1 minus x squared times itself 3 times, that entire big huge polynomial is down here on the bottom. If I bring it up to the top, it's to the negative first power. And I cannot distribute that x when I've got a power other than 1 right here. Don't you do exponents before you do multiplication? Well, what the heck are you going to do with an exponent? Well, if I move it down, then I can't split up the fraction. Do you see the problem?
Could you still use?
Do you see the problem?
There's a lot of them.
The problem is that we can't make this function or this integral look like the sheet with just algebra. The problem is that this is going to require some other type of technique.
That was a trick question.
I know. I wanted you to feel the suffering. The suffering of trying to fit a square peg in a round hole. It ain't going to fit. So you need to figure out another technique. Now I want to make sure that you understand in this new process that we're about to discuss, I've still got the same goal in mind. I've still got to still got to work on this thing in some form or fashion to make it look like the rules on the sheet. That's still my goal, but I'm going to use a different process besides algebra to make that happen. All of the integrals that you're about to see are not yet sheet worthy and cannot be adjusted using algebra. All the ones you're about to see, I'm just going to scroll through them for a minute, we're going to need another process.
We're gonna take another derivative.
So we need to write this in.
I'm going to get to them one by one. I just want you to look at them. Just chew on them a minute.
Feel the burn.
Well, you know, I could rewrite this as, I could use some algebra. Yeah, I could. I could make it look like that, and I could make it look like, okay, I could use some algebra and rewrite it like that. Just a little bit of algebra. But it still doesn't look like the sheet. You got that on the sheet anywhere? What you got on the sheet? E to the x. Just e to the x. That is not e to the x, and I can't make it be e to the x. Yeah, we can do something else. Maybe like a sort of kind of chain rule. That one, I can't do anything to it. It's kind of like the one we just talked about earlier. All of these. Why can't I use why can't I use the sheet with that?
Because there's no.
Is that 2x over?
Because the 2/3. That's right. Well, isn't the 2/3 a constant?
It's inside the trig.
It's not a constant. That's right. It's part of the angle measure. The 2/3 is part of the angle measure, so I can't pull it out as a constant. And we dang sure don't have a square root on that sheet. I'm going to have to do something with square roots. And I'm going to wait for that one the next week. Okay, so we got to come up with some idea. All right.
I have a feeling it's going to involve E or laws.
Eat what?
Either E or natural laws.
No, it won't.
I have a feeling we're gonna slap ourselves in the head. Trying to
No, it's not really that bad. It's not that bad if you understand it. I'm sorry. I don't know what else to tell you. I love it. You may not, but just hold on just a minute.
Well, we established your kind of person who likes Chattanooga,
Well, you
so
said
we're already
like-
kind of iffy.
Some sort of chain rule.
Kind of like the backwards chain rule, sort of. I mean, you already know about derivatives, that you got to use the chain rule when it's not just a basic formula. So this is kind of like, sort of, the chain rule for integration. Do you see that if I took the derivative of x squared, that I would get an x somewhere in there? I'd get negative 2x, but I would get a negative x.
Yeah.
Okay, so I'm going to do something called integration by substitution. Not the chain rule, but it's what we call using substitution to find an antiderivative. This is one of about 6 different integration techniques. You'll learn the other ones in Cal 2.
Yay.
So, follow my train of thought, and then I'll go back to the beginning and show you what I did and why I did it. I'm going to use the U letter. You used U's in the chain rule, right? So you're very familiar with the idea of U's. And I'm going to let U be a piece of this integrand. And specifically, this is the part that takes practice, trying to figure out what to let U be. I'm going to let U be 1 minus x squared. You could have attempted to let U be x. You could try to let U be 1 minus x squared to the quantity cubed, but after a while, you'll see that it's not going to work. So I'm going to do it the working way, and then I'll go back and show you why it wouldn't have worked to let U be anything else, okay? The next thing I want to do is I want to find the derivative of U with respect to x. The notation here is very, very, very important.
So he was right. You want to find the second derivative?
We're going to find a derivative. Yeah, not the second derivative, but we are going to find a derivative. Yeah, derivative is part of it. So the derivative of du with respect to x is negative 2x. This dx right here is this dx. They're the same. I want to know what dx equals. So I'm going to solve this equation for dx. So I'm going to write it in its differential form. I'm simply multiplying both sides of the equation by dx. That's its differential form. I'm solving for dx. So I'm going to divide both sides by negative 2x. Okay? Dx is equal to du over negative 2x. So, by substitution, this is why it's called substitution. I'm going to take this integral, and where I see the dx, I'm going to substitute du over 2x squared in its place. Du over negative 2x in its place. That used to be the dx. That used to be the dx. Now my integrand, I've got an x up top, but on the bottom, where I used to have 1 minus x squared quantity cubed, I've let u be 1 minus x squared. So what should I write here?
It went away.
Bye-bye.
It's gone.
So, use some algebra. Tell me what I can do.
Cross multiply.
Not cross multiply, but I know what you're thinking, but it's not cross multiplication.
Cross factor. Cancel it out.
I can reduce or cancel. The x's are gone, aren't they?
Yep.
The u. Wait, no, you know that.
Can't cancel. This u is not this u. This is a du. It's a differential, so I can't cancel those out. But look what I've got. Do you see a constant?
Oh, yeah.
What is the constant that I can pull out?
2.
Negative 1/2? Everybody see the negative 1/2? There's a 1. There's a 1 right here. There's an understood 1. So I've got a negative 1/2 that I'm pulling out front. And I'm finding the integral of 1 over u cubed du. Is that on your sheet? Is that anywhere on your sheet? U's instead of x's.
Oh.
Natural log.
Natural log is just 1 over x, or 1 over u.
Find number 9.
Number 9 is the power rule, but I don't have a fraction. So we're not sheet worthy yet. Okay? You want me to do anything to get it ready for the sheet?
U -3.
Negative 3, yes. Aha. So if you mentally imagined that these u's were x's, can we use the sheet now? Rule number 9, isn't it? Rule number 9. So this is negative 1/2 times u to the negative second over negative 2 plus c. You just use the sheet, so the integral symbol's gone.
So now you put in
Did you substitute that?
Right. You substitute your 1 minus x squared back in for u. You started off with x's. You got to end up with x's. So my actual antiderivative is 1 minus x squared to the negative second power all over negative 2 plus c. Now you could simplify that really easy if you wanted to. You may not want to, but that would just simply be what? Negative 1 over No, it's going to be positive, isn't it? We'll have a 1 over 4 times 1 minus x squared plus c would be the simplified version if you don't want to go to the trouble of typing all that in. So let me go back to what I did. This is the idea of substitution. You have got to pick something for you such that when you find the derivative and solve for dx, it makes something cancel out. Something, like with the x's, to cancel out to get you an integrand in terms of u that looks like the rules on your sheet. That's the point. So I could see, because I've been doing this for 30 years, I could see that if I picked what was inside the parentheses here and took the derivative of something squared, I'm going to get something to the first power, and maybe that would cancel with that x to the first. But if I tried something else, because I am not saying by any stretch of the imagination that there's only one way to do this, but let me show you what happens if you try to let something else be you. Yeah. So, I don't know, rule of thumb, you're never going to let u be x. Never, never, never. Because if you let u be x, then substitution is not going to work in the first place. Okay? Yeah. U, x, okay, you're just substituting variables. You're never going to do that. So the only other thing that you might let u be in this case would maybe, let's let u be 1 minus x squared to the third power, the entire denominator. Let's just try that and see what happens. So, next thing I do is take the derivative. You're good at this now. You're real good at this now. Talk to me.
1 minus x squared, 2.
Times negative 2x. Okay. Let me rewrite that a little bit simpler now. I like to simplify it. So that's negative 6x times 1 minus x squared, right? So that means that I'm solving for dx. Now I'm solving for dx because this dx, remember, is this dx. So when I solve for dx, I've got dx is du over negative 6x times 1 minus x squared, and now I'm ready to substitute back in. Everywhere I see a dx, I'm going to put this in its place, up top. So that would mean, have way out here, I'd have a du over negative 6x times 1 minus x squared, and then I've got an x up top, and I've got a u cubed on the bottom, right? That's the substitution.
Be a u.
Just you.
It's just a u.
Oh, just u. All right, y'all fight over that one. Okay, so now what do I do?
You can't do the thing that you did.
I can cancel something though, can I?
Cancel the x on top.
I can cancel the x here and here. But I can't get rid of this, can I? I can't get rid of the 1 minus x squared. And the problem is that none of those rules on your sheet, none of them have two variables. Do they? They're all x's and dx's. So the fact of the matter is that if I'm integrating with respect to u, du, integrating with respect to u, I better have nothing but u's in my integrand. So the moral of the story is, I've done the substitution correct. There's nothing I've done wrong here. it just doesn't help me, what I've done here. It doesn't get me to the sheet. It's good work. It's quite beautiful, but it's not going to help me any. The practice that you need to get into is figuring out what to let you be. That's going to take some practice. And so that's what I've got planned for the remainder of the night. We're going to work together to try to determine what U is going to be and then work through the process of substitution. We've already determined it's not on the formula sheet. What do you want to try? It's okay to make mistakes. If you're going to make mistakes, make them now.
Equal to the denominator.
E to the 2x. All right, that's worth a try. Let's let U be e to the 2x. We're finding the derivative. That's written as du dx, and that's 2e to the 2x. Everybody knows the chain rule. I'm solving for dx, and I'm going to stop and let you look at it. Make sure you're okay to right there.
No,
What's wrong?
I don't think it's going to work.
You're already looking ahead, you don't think it's going to work, but am I okay to this point? I mean, mathematically, I'm all right with what you let be U. Now, Rachel, you're already getting good at it. Why do you think this is not going to work?
Because it's not just one thing. It's like when you try to cancel it out, like you're still going to have more.
We're going to have something left, aren't we?
Yeah.
So I'll have 5 minus e to the x divided by U times du over 2e to the 2x.
We would need e to the 2x to be on the top to cancel out.
Yeah, I can't, this is not going to cancel though. Go ahead, William, he just had a thought.
Yeah.
Let U be e to the x?
Yeah.
All right, let's try that. I'm up for anything.
That was my idea, which I didn't really push, but are we going to be able to cancel if it's up there?
I don't know. Hey, you know what? If you want to let U be e to the x, you might as well let U be 5 minus e to the x. Because when you take the derivative of 5, you get 0.
Well, I was thinking that you
Okay, I'm going to go with what you want to do. Okay. He wants to let U be e to the x. I got you. Let's just see what happens. So du dx is e to the x, right? I'm going to start skipping some steps now. So dx, I'm just doing algebra here. This is just algebra. William, you all right with that?
Yeah.
Okay, now we're going to try to substitute back in. So I've got the integral of 5 minus u divided by,
U squared.
oh, you want to put u squared.
Yeah.
Okay. Because e to the 2x is e to the x squared.
Yeah.
I got you. Oh, you want to put u here? You let u be e to the x.
Yeah, sure.
I mean, you let u. I can't leave it like that
Yeah.
because I can't. Can't have x's and u's. All right. Well, he's accomplished one big thing, hasn't he?
Cleaned out the x's.
All the x's are gone. That's pretty doggone good that he got rid of all the x's. Can I cancel the u's?
No.
No, but could I multiply the u's?
Yeah.
Sure.
That's the,
On the sheet? No? Can you do any algebra to it?
Bring the U up.
You could bring the U up, or you could do some fourth grade math, hint, hint, fourth grade math.
5 over U cubed minus U over U cubed.
This is equal to 5 over U cubed minus, can I call it 1 over U?
1 over U squared.
Whenever you square.
Oh, squared, sorry.
No.
No, that's interesting. We've got squared and cubed up there.
Oh, I'm sorry, it is cubed.
Yeah.
You're freaking me out now. And then U over U cubed is 1 over U squared.
Yeah. Yep. That's the one I was talking about when I said
Okay,
squared.
got it. Hey, are we getting there? Right, let's keep it churning.
So can we pull that 5 out front yet?
Sure.
Can we pull that 5 up?
Why can't you do that now?
If we split it.
We split it up into 2 fractions. Let me rewrite this so everybody sees why. You all right with me doing this?
5 times 1 over.
There you go, okay.
Well, now those are both the same as U to the negative, aren't they?
Ah, okay, so you're already knowing to make it a power. I have not used the sheet yet, therefore I'm continuing to use my integral symbols.
Now we can use the sheet then.
Now we're ready. We have forced this integrand to look exactly like the sheet with nothing but u's. So I've got 5 times u to the negative second over negative 2 minus u to the negative first over negative 1 plus c.
Do we need to substitute back into the U?
Absolutely. If you start with x's, you got to end with x's. What did you let u be, e to the x? Okay, so that's, let me clean this up a little bit first. This is
Negative 5.
2u squared plus 1 over u. Okay, so that's negative 5 over 2, can e to the 2x, okay? Plus 1 over e to the x plus c. William, it looks like your eureka moment turned out to work pretty well.
Would that be messier if U was 5 minus e to the x? Back at the beginning, you suggested getting rid of the constant that way.
Yeah, hold on, let me let everybody make sure that they understand where I got here, and I'll go back and look. My suggestion was to let u be 5 minus e to the x. And if you had done that,
Basically get rid of all.
these would have canceled out, right?
Yeah.
These would have canceled out together, and then you would have just had to use the power rule once. But, you know, it works. Hey, if it works, it works. You'll know if it doesn't work because you would have substituted everything back in and you'll be sitting there looking at u's and x's. You may not use that sheet if your integrand has 2 variables at all. You may not use that sheet if your integrand doesn't look exactly like what's on that sheet. So I'm going to put William here. I wouldn't have done it this way, but shoot, it works out. Whatever works for government work, right? William E. works for me. Whatever works, go for it. I like it. Trust your instincts. And don't be making crap up. Because if you get somewhere and you feel like you're making it up, you probably are. Right? Let's try to... I think this is like the first one. It actually may be the first one. No, it's not either. The point is that we cannot use algebra in any shape, form, or fashion to make this integrand look like a sheet. And our only other technique for integration in this class to date is substitution. So, what do you think?
It says ditto.
Yeah, ditto, like we gotta have something else. The only other procedure we have is substitution.
So what, u equal 5 minus x cubed?
Okay, so Mike, why do you have an educated guess, or is that an educated guess? And can you tell me what you're thinking?
Trying to get rid of the constant.
What constant?
Or trying to get rid of the number that's by itself that doesn't have a variable. At this
Okay,
point.
so you're talking about the 5. All right. As we go through this just a minute, think about at the end why that makes sense in red.
Because we're about to take the derivative of it, we're going to get rid of it.
We're going to get rid of what?
5, right?
We're going to get rid of the 5 when we take the derivative, but look what else happens when we take the derivative. Yes, the 5 definitely will disappear, but the derivative is 3x squared.
Whatever we choose squared. Ooh, that's great.
Squared. Something might cancel out here, right? So if du over dx is negative 3x squared, then dx is du over negative 3x squared. I'm now ready to substitute back in. Everywhere I see a dx, I'm putting du over negative 3x squared. Got x squared up top, I've got u on the bottom. What happens?
Your x squares, or cancel out.
X squares cancel. And I can simply, you see a constant?
Negative 1/3.
Negative 1/3 is the constant that we're pulling out front. And this baby in blue is on the sheet.
That's the natural one.
It is the natural log rule. Yes, it is.
Because of how it works whenever we take the derivative and how it always ends up on the bottom of a fraction, or usually, it's usually better to take the bottom. And then cancel it out.
I'm not going to get painted into that corner. I'm not going there because I think there will be situations where that just won't work. I'm scared to say. I mean, in these types of situations where it's a rational function and your degree on the bottom is bigger than the degree on the top, yeah. But it won't always be that way. So what is the antiderivative?
The natural log, 1/3.
Negative 1/3 times the natural log of u plus c.
Absolute value of u, because it's we don't have boundaries.
No, we don't have boundaries, so u might be and have a negative value within the boundary. So negative 1/3 times the natural log of 5 minus x squared cubed, which could be a negative depending on what you substituted for x. I think I've picked some that get a little bit more difficult for you to figure out what to let u be. I hope I did. Okay, 3 more. Takes practice. Hmm?
X
Are you asleep back there? Are you asleep back
I
there?
don't know, I thought that was f of x of cosine x.
Oh, yeah, yeah. What would y'all like you to be?
X squared.
Why are you picking x squared?
Because then that X right there.
Ah, so you're already in your brain thinking about taking the derivative of x squared, that the derivative would have an x in it, and maybe that derivative would cancel with that x. All right, maybe. Let's check. Du dx is 2x. So we're solving for dx. I'm just doing algebra to solve for dx. I'm just doing algebra, just a couple of steps in my head here. So we've got x times the cosine of u du over 2x.
And that's basically just that over 1.
What's that over 1? What do you mean?
Like that X cosine u, you just throw that.
Oh yeah, it's all over 1. That's correct. Yes.
So cancel out that?
She says that she's looking at a fraction here over 1. That's right, Rachel.
Cancel out that?
Cancel our x's.
We'll have a 1/2.
Everybody see where he's getting the 1/2 as the constant? The 1/2 there is an understood 1 right here beside the du. So we've got cosine of u du, and there it is. Look at that. It's right there in front of your face, isn't it? You know the antiderivative of the cosine of u du. It's what? The sine of u. This is an indefinite integral, so I've got to put my plus c. And then lastly, substitute. Substitute back in. That's right.
Because we're choosing X as our U, we don't have to put it in place of X in the first.
Say again?
No, x squared is different.
Now I got to warn you about something just a minute before we do these last two problems. The way I do substitution is the way I learned to do substitution and the way that I'm successful at doing substitution. Let me warn you, are you listening? If you hit that watch it video, that watch it button this week, they're not going to do it like this. You might like it better, what they do. I don't know. But they're going to do something that they have to do a little bit of tweaking to make things fit just where they're supposed to go. So, if you watch the videos and it doesn't make sense what they're doing, it doesn't make sense for a reason, because that's not how I do it. Okay?
Some of those videos, they don't explain anything.
They don't explain anything hardly, do they? They just start writing. It's like they're just reading off a script and just writing as they go. It's a pretty good gig, though. If anybody wants to do it, I bet Website will pay you big money to do it. Crystal?
When you say like plug it back in, where exactly plug it in? Because it's supposed to-
Are you saying right from here to here? Well, you know, remember we let u be x squared. We let this variable that we called u, we let it be x squared. So when we found our antiderivative here, in the terms of u, I need to put something in the place of u. Well, what am I going to put? X squared, because that's what u equals. Substituting it back in.
Because we have to end with X, not U.
Yeah, since we started with x's, since our integrand started with x's, I got to end up with x's.
Behind you.
Now,
Behind you.
behind me. Yes, sir.
Is there a rule of thumb for like choosing what you want to substitute for what you want to use for u, or is it all just kind of trial and error?
Well, you never want to pick something that's too long. I mean, you don't want, if you've got a polynomial and it's raised to a power, you just want to pick the polynomial. Don't pick the polynomial raised to the power, because you've got to take the derivative of the sucker. And when you take its derivative, that's going to get ugly if you have to use this chain rule over and over and over again to find the derivative. So pick the simplest thing possible try to do what Rachel was doing and thinking ahead to determine if anything's going to cancel out. You know, and you're so good now at finding a derivative that you can think about derivatives ahead of the game and know what's possibly going to happen when you cancel things out. If you get stuck in a situation where you just don't know what to let u be, just do what you did and just try something. You'll know if it's not going to work, and then you can pick something else. But you never want to let u be x, because substitution is not required if you let u be x.
You're just adding steps and not doing anything.
Yeah, you're just changing your variable name. You're changing all the u's to x's, which doesn't make any sense. You're still not going to be sheet worthy.
Ain't gonna be worth a sheet.
What's that?
So it ain't gonna be worth a sheet.
It's not going to be worth the sheet the print's written on. That's right. Now this one's a little different. What's different about it? Yeah, we got boundaries this time.
Didn't change anything.
Well, it changes the way our answer will look. Because when Crystal and I were just talking, that in an indefinite integral, if you start out with x's, you got to end with x's. But with a definite integral, you're going to end up with what?
Numbers.
Numbers. So no matter what happens, I'm going to get numbers for the answer. I'm looking for the area under a curve. Well, I've already discussed earlier that this does not equal this. I want to make sure everybody understands and remembers their trig, that 2/3 is part of the angle measure. It is not a constant, therefore you may not pull it out front. These two do not equal. Notice the do not equal signs here. So if that's the case, if I can't pull the 2/3 out, then my integrand does not look like what's on the sheet. You only have one choice in Cal 1, and it is?
Substitute.
That's your only choice is substitution. That's all you got right now is substitution as your alternative. Ideas?
Substitute 2x over 3.
Yeah. But you're not going to let u be the whole thing, are you? If you're going to let u be the whole thing, whether you...
That'd be really easy.
Yeah. So let's let u be 2x over 3. So du dx would be 2/3. And dx would be 3 du over 2. So I'm just using algebra now. This is just algebra, these last two steps. Or excuse me, this last step.
The derivative is 2/3?
Yeah, because this is 2/3 times x. This is the same thing as 2/3 times x. Now something weird's about to happen. I'm about to do something wrong, and I want you to tell me what it is. Warning. Everett's about to do something wrong, and she knows she's about to do something wrong.
Left the parentheses off for cosine u.
Sir?
Left the parentheses off for cosine u.
You don't really need to know.
Oh.
I mean, I guess it could.
Is cosine u still over 1?
It could, yeah. It's understood to be over 1. You don't see it yet?
You don't change cosine to
Does it
sine?
have to do with the boundaries?
Talk to me about that.
Well, you're still dealing with cosine, so I didn't know that you'd have to change that any. But
I agree with you that it has to do with boundaries, but not for that reason.
do we have to convert the boundary since it's 2/3 x, u equals 2/3 x, and if we're going to have cosine of u, we need to change the boundaries to reflect that?
Reflect what?
That if you punch in the numbers, you'll get the same result from cosine. Do you have to change the pi and the...
To what?
So that when you put it in for 2/3 x, when you put it in for u, it's the same as putting it in for 2/3 x.
So these boundaries right here are boundaries for what variable?
For x.
Ah. Ah. That's it.
Huh?
Oh, okay, just a minute. Look what's going on. The 0 and the pi are boundaries for our x variable. Right? Okay, let me keep making a mistake. Don't write this down. I'm going to keep making the mistake, and you're going to see what he's talking about. I'm going to keep going. This feels good. Feels good to put a 0 and pi up there, so I'm going to keep going with it. I'm going to pull that 3/2 out front. I got a cosine of u du. Hot dog. That feels even better because that is sheet worthy. This is 3/2 times the sine of u. I don't need a c because I'm finding a definite integral.
And we're putting the numbers in before we undo the substitution.
And let's just go ahead and substitute pi in for u. If it feels good to do it, might as well.
But we can't do
U
that.
not pi.
We can't do that because we've got to resubstitute in 3du.
0 and pi are values of what?
X.
Those are values of x, not
U.
u. Get it?
This is 2 pi
So I
3.
said in the very beginning, I said I had made a mistake right here. I need different boundaries. If I'm trying to create an integrand that's in terms of u, then I need boundaries that are boundaries for u. Does that make sense?
Yeah, you gotta have X.
Okay, so I am going to erase these boundaries.
So what do you want to do?
And I want them to be u values.
Degrees?
So it's
2/3.
that would be different.
Right here.
Can be 3.
So the equivalent.
So when x is pi, my upper boundary is where x is pi.
Oh, just plug it in.
Plug it in. Absolutely. You're telling the relationship right here between 2 and x. So when x is pi, u is 2 pi over 3.
We do get to keep the 0, right?
Okay, so when x is 0, u is 0. All right, does that make sense? Notice the notation. If you leave 0 to pi, it is just flat out wrong. It doesn't make sense to have boundaries for x when you're integrating with respect to u. William?
Never mind.
Was the rest of that stuff right though?
Well, when you get down to down there, to the
Let me hold that thought. Let me erase and get everything correct. Down to here.
yeah.
Okay.
Can't you just circumvent all that by resubstituting your u value, or because
You're good. You're really good. Dang right, man. Hold on a second. Let me write this in, and we'll talk about what you're saying. Do I understand you correctly, William, that you would rather use 0 and pi as your boundaries?
yeah.
You don't want to go to the trouble of recalculating your boundaries in terms of u.
Yeah.
You would rather go down through here and do substitution like you know how to do, and when you found your antiderivative, you would rather substitute 2/3 x over 3 for u. Y'all following me?
Mm-hmm.
If he does that, then he may use 0 and pi. That's perfectly fine. But warning, if you do that, if you choose not to change your numerical boundaries to u boundaries, then you must leave these blank while you're integrating. You see what I mean? You got to leave these blank for a while until you substitute the 2x over 3 back into your antiderivative in order to use the fundamental theorem of calculus. It makes no sense to use 0 and pi in the midst of trying to calculate with u's. That's right.
So, okay, I was wondering if there's a notation problem. You just leave it off?
Leave it off for a while. You're just trying to find an antiderivative. You're looking for an antiderivative, and when you get down to the bottom, he's going to substitute 2x over 3 back in for u, and then he can use the 0 and pi for his x boundaries.
Okay, so if you're taking that off, remember to look back at your original problem.
Yes.
So that you give the correct answer.
But do you see, though, Okay, just a second. I got to give you a word of advice. Big word of advice. What I see most often, the mistake I see most often in this case, definite integrals involving substitution. People forget to substitute back in. You're knee deep in substitution, okay? You are knee deep. It has taken you a page to get the sucker sheet worthy. And all of a sudden you're down here, you found an antiderivative. Whew. Let's just use the fundamental theorem of calculus and substitute in. You see what I mean? So if you go ahead and take care of the boundary issue, you don't have to worry about anything else but just substituting when you get down to the antiderivative. But I see that problem most often. I've made that mistake when I don't change my boundaries to U boundaries. Are we speaking the same language? Okay, so I guess we got trig functions, so I need some actual values. What's the sign of 2 pi over 3? Something positive.
I was going to ask you to tell us the integral again.
What is it?
Radical 3 over 2.
Square root of 3 over 2? Yeah, I agree with that. And the sign of 0 is just 0, right? Yeah. Last one. I think. Let me check it. Oh yeah, this is the last one. The question of the day is this thing, does this thing look like anything on your sheet? No. So is there anything we can do to it, algebra-wise, to make it look like a formula on the sheet? How about distributing? You want to distribute the x cubed? Well, it's tempting though, isn't it?
No.
Can't do it. But it's tempting. Can't do it.
Oh, okay.
Even if we did it, we couldn't help us any. We would still have a problem. We all agree that substitution is required? Are you good enough now to tell me what I should let u equal? X to the 4th plus 5. Now, why didn't you just stop at x to the 4th, Sarah? Yeah, I mean, you might as well just add 5 to it because you're going to take the derivative of it. It's going to be 0, right? Paul?
Someone asked about rules of thumb or guidelines or anything. The thing that caught my eye was, well, they're different by one
degree.
They're different by 1 degree. So grab the larger one and it'll take care of the smaller one after we differentiate.
After you find the derivative. That's right. That's right. You're already getting good at that. Good. So let's let u be x to the 4th plus 5.
Now,
I'm listening.
I'll cover it after we do the substitution.
Okay, so du dx is 4x cubed. Solving for dx, du over 4x cubed. My pen is so tired, as I am so tired. So we're ready to substitute back in. You know what I mean, Crystal, about substituting back in here, correct? Let's talk about that, because I was just substituting back in at the end earlier. You see this dx right here? That dx is this dx. So in the place of that dx, I'm going to put du over 4x cubed. All right? So I've got my integral symbol way over here. In the place of dx, I'm going to put du over 4x cubed. Now I've got an x cubed, and then I've got a square root of what I called u. That's another substitution. I let everything, using Sarah's idea, I let everything underneath the radical be my u. So I'm literally going to put u in the place, substitute u in the place of x to the 4th plus 5.
Can we just raise that to the 1?
Ma'am?
Can we just raise that to the 1.5?
Okay, you want me to change that to the 1/2 because I don't have a radical. All right, what else?
And cancel out that x. Oh.
The x cubes. Good.
Bring the
And you
1/4
got
out.
1/4 comes out front.
Now we're
And then something so simple.
Are we ready?
good.
Yeah, you can do that rule.
Which rule?
Number 9.
Number 9. Hey, number 9 doesn't say that n has to be an integer. N can be a fraction. N can be a decimal.
That earlier was, we don't have a rule for a square root.
Oh,
We do
okay.
have a rule for n, whether or not it's an integer, for variable to the nth.
Uh-huh. Fractions are our friends. Please let's simplify this because I would never want to have to enter this into WebAssign. How about
Is it like 2 times?
Isn't that 2u to the
Flipping.
2 seconds over 3?
multiplying? Right? What did I do wrong? Did I add wrong? Flipping and multiplying. What did you say? 2/3? So 2/3 u to the 3/2, and we let u be what?
What happened to the,
We missed
The what?
1/4? We have
Oh, I took the 3/2 and I flipped it and I multiplied it times 1/4. 1/4 times 2/3 is, oh,
2/12. 1/6.
Is 2.
I don't know, what is it?
1/6.
Okay, 2/12 to 1/6, sorry. You were telling me to flip it and make it 2/3, right, Nick, and then multiply it. I just completely missed the multiplying. 2/12 or 1/6?
Yep.
Thank you, and I let you be what? I don't see it up there.
X, 4 plus 5.
X to the 4th plus 5. This week you'll be practicing with some substitution as well as some basic rules. The plan for next week, which will be the last night we meet before test 3. Hey, do you understand, people, that after tonight we only meet, how many more times we meet? 3?
Twice, not.
We only meet 3 times after this. And that includes your final exam?
3 including the exam. The 8th, 15th.
Next week's the 8th, the 15th,
And the 22nd. is the
22nd.
exam.
Oh, and then y'all have your final exam the next week.
We have a quiz, and then I guess we'll review and then stop by.
Wait a minute. When's your final exam is on the 22nd?
Yes, it's 3 including the final.
3 days, that's all we got left. Next week, we do some inverse trig. We do something with bases other than E. And then the majority of our time next week will be y'all working together to integrate using substitution with some that are quite challenging. These were not challenging, okay? So you'll be doing a lot of work next week together on doing some substitution with breaking up into small groups.
We have a quiz.
You have a quiz next week. The first part is just the basic formulas. The second part is applying the formulas, okay? Like what we were just doing. They won't be any more difficult than this. They won't be as difficult as the concepts for the lectures next week, but you will need to know how to at least apply these rules. I think there are a few people in here who need me to look at your test, and there are a few people who need to get me to sign some tabs, and I will
So
see
you
you.
added sheets from the homework?
Oh yeah, you want to do that? Homework, extra credit. If you're staying, then you want to do the extra credit for homework. Otherwise, everybody else, I'll see you next week.
Oh, yeah.